Hello friends, how are you? I hope you are doing fine. So friends, our today's topic is RLC series AC circuit. In this circuit, we are connecting resistor, inductor and capacitor in series with a single phase AC supply. Okay, so how your circuit will look like? Your circuit will consist of a resistor, then inductor and then capacitor. All these are connected in series across a single phase AC supply like this. So when we turn on this AC supply, what happens? Current starts to flow through this circuit. We are calling this current as current I. When this current passes through all these components, voltage is developed across resistor, inductor and capacitor. So we are getting three different voltages. We are calling it as VR, voltage across resistor, VL, voltage across inductor and VC, voltage across capacitor. Okay, and all these values can be written according to the Ohm's law. So what we are getting, VR is what? I into R. So we know that for purely resistive circuit, voltage and current are in phase. So your VR is in phase with your current flowing through the circuit. Then VC is nothing but I into XC, current multiplied by reactance of capacitor. So we know that in case of capacitance, voltage is lagging by 90 degree with respect to current. And then finally VL. So VL is I into XL. We know that in case of inductance, voltage is leading with respect to current by how many? 90 degrees. Okay, and capital V is nothing but the RMS value of applied AC voltage. Okay, and capital I is nothing but the current flowing through the circuit. Okay, so these are our circuit parameters. Okay, now our next aim is to draw phasor diagram for this circuit. So for that purpose, first of all we will study the individual phasor diagrams for purely resistive circuit, purely inductive circuit and purely capacitive circuit. So friends, now you are aware that in case of purely resistive circuit, your voltage and current are in phase, so they will overlap on each other. So they are having phase difference of 0 degrees. So that we have seen over here, we know that in case of purely resistive circuit, your voltage and current are in phase. Now in case of purely inductive circuit, your voltage is leading with respect to current by how many degrees? By 90 degrees. So here we have seen voltage is leading with respect to current by 90 degrees. And finally you are having capacitor. We know that in capacitor, voltage is lagging with respect to current. So if this is your current, voltage will be lagging. So we have to show it in downward direction. Now if we superimpose all these phasor diagram on each other, so what you are getting? So friends, you have to remember that on x-axis you have to take the parameter which is common to resistor, inductor and capacitor. So if you look at this circuit diagram, you will find out that current is common to resistor, inductor and capacitor, whereas voltage is different for R, L and C. So what we are doing, we are taking current on x-axis. So always you have to take the quantity which is common on x-axis. Now you know that voltage across resistor and current are in phase. So your voltage and current will overlap each other. So they are having phase difference of 0 degree. Now we are having current as a reference. And if you want to draw the voltage across inductor, so what you are getting, if current is on x-axis, voltage will be on positive y-axis because we are having phase difference of plus 90 degree. Okay, means voltage is leading with respect to current by 90 degree in case of inductance. And similarly, if you take case of capacitance, your voltage is lagging, so we are showing the voltage on downward direction. Okay, and what is the phase difference? Minus 90 degree. So in this way you are getting phasor diagram for RLC circuit by combining all these three phasor diagrams. Okay, so friends, if you carefully observe this phasor diagram, what you will find out, voltage across inductor is in positive y direction, whereas voltage across capacitor is in negative y direction. Means they are opposite to each other. Okay, so whether your circuit will be resistive, inductive or capacitive, it will be decided by the values of VL and VC. If suppose your VL is greater than VC, means voltage across inductor is higher than voltage across capacitor, so your resultant phasor diagram will be in positive direction. It means what? When your VL is greater than VC, your circuit will be, overall circuit will be inductive. Similarly, if your VC is greater than VL, means voltage across capacitor is higher, then your circuit will be capacitive. And again there is a third case, if your VL and VC are exactly similar to each other, what will happen? VL and VC will cancel out each other, and then in that case only voltage remaining is voltage across resistance. In that case your circuit will act as a resistive circuit. Okay, so for our understanding we are considering first case. We are assuming that voltage across inductor is higher than voltage across capacitor. So you will get the phasor diagram like this. So this is your current, then this is your voltage across resistor, current, then voltage across resistor, and now VL and VC are opposite to each other, and we are considering that VL is greater than VC. So your resultant phasor diagram will be in positive y direction. Okay, so you are getting the voltage VL minus VC. Now for calculating total voltage V, what we have to do? From the end point of VL minus VC, we are taking horizontal projection like this. From the end point of VR, we are taking vertical projection like this. And whatever intersection point we are getting, we are combining those 2 points and with respect to origin, and then whatever phasor we are getting, that is nothing but the your applied voltage V. Means your applied voltage V is combination of VR then VL minus VC. Means your total voltage will be decided by VR and difference of VL and VC. Okay, so if you carefully look at this, what you will observe that VR is on x-axis but VL minus VC is on y-axis. Okay, so if two quantities are on different axes, we cannot add them directly. In that case we have to use phasor addition or vector addition. Okay, means this your voltage V is due to the combination of VR and VL minus VC, but while writing the value of V, we have to take phasor sum. So how we can take phasor sum? So for taking phasor sum, suppose you want to find out the value of V, then your V will be, for taking phasor sum, what you have to do? You have to take square root. Okay, so you are getting this square root, and inside this square root you are getting squares of these two parameters. Your V is due to what? VR, so you are taking square of VR, and another parameter is VL minus VC. So VL minus VC bracket square, and all these you have to take inside this square root. Okay, now in the beginning we have written the values of VR, VL and VC. Okay, now we are putting those values. Okay, so friends, after putting the values of VR, what is your VR? I into R, so it's square. Then VL is I into XL and VC is I into XC. Okay, after putting these values, the common parameter is I. Okay, so we are, and it is having square, so we are taking I square outside. So when square comes out of the root, we are getting I, and in the root the quantity remaining are R square plus XL minus XC bracket square. Okay, now if you take this quantity in the root, on the other side what you are getting? Current. So current is equal to voltage divided by square root of R square plus XL minus XC. Now this is nothing but your impedance. Okay, because your circuit consists of resistance, inductance and capacitance. All these three parameters will try to oppose the current. Okay, and the total opposition to the flow of current is nothing but your impedance. So what is your current? Total voltage upon total impedance, and impedance is nothing but combination of resistance and reactance. So here we are having two different reactances, capacitive reactance and inductive reactance. Okay, so this parameter is nothing but your impedance, and resistance, XL and XC, all these three parameters are measured in ohm. Okay, so your unit for this impedance is also ohm, and impedance indicates total opposition to the flow of current. So this is about the basic information about this circuit. Now we will study various parameters related to this RLC circuit. Okay, so friends, our first parameter is nothing but phase angle or phase difference. It is indicated by phi. Okay, now phase difference will depend upon the nature of the circuit, behavior of the circuit, and behavior of this circuit will be decided by the value of VL and VC. If your VL is greater than VC, your circuit will be inductive. If Vc is greater than VL, circuit will be capacitive, and if they are equal, then your circuit is resistive. Okay, so here we are considering that VL is greater than Vc, means your circuit is inductive, and we know that in inductive circuit voltage is leading, current is lagging. So friends, we are assuming that circuit is inductive. So first of all, we are drawing the phasor diagram for voltage. So your voltage will start from 0 degree. Okay. So your sinusoidal voltage will look like this. And if your circuit is inductive, then definitely what will happen? Voltage is leading, current is lagging. So what happens if voltage is starting at 0 degree? Current will start after voltage. Okay, and what will be the phase difference? Your phase difference will be phi, and the value of phi will depend upon the value of inductance and resistance. Okay, so now what is happening? Your current is lagging. Okay, so the second waveform we are looking at is nothing but your current. And if you compare these two waveforms, what you will find out, their starting point has a gap of 5 degrees. Okay, starting point has a gap of 5 degrees. So this is nothing but the phase difference between voltage and current, and this is the case when your circuit is inductive. Now if you are looking at the second case, now what we are assuming over here, Vc is greater than VL. So this indicates that circuit is capacitive because Vc is higher. Okay, and first of all we will draw the phasor diagram, waveform for voltage. So suppose your voltage is starting from 0 degree. Now we know that in case of capacitive circuit, current is leading. So if voltage is starting at 0 degree, current should start somewhat earlier. So we are showing that current is starting before voltage because current is leading in capacitive circuit. So you will get the waveform for current like this. And if you compare their starting point, what you will observe, they are having a gap of 5 degrees. They are having a gap of 5 degrees. Okay, and this 5 will be anything in between 0 to 90 degrees. Okay, your phase difference is always in between 0 to 90 degrees. And here your current is leading. In case of inductive circuit, voltage is leading. Okay, in case of this capacitive circuit, your current will lead. Okay, and now if we consider the third case, now what we have taken over here, VL is greater than VC. Here we are considering VC is greater than VL. Now if we consider the third case, now what we are assuming, VL is equal to VC, means both voltages are same. So in that case, your VL and VC are opposing each other, so they will cancel out each other, and what you will get, so if suppose this is your voltage, now since VL is equal to VC, your circuit is resistive, and we know that in resistive circuit, voltage and current are in phase. So what happens, you will get the waveform like this. So this is nothing but your voltage, and this is nothing but your current. So what is happening over here, when VL is greater than VC, circuit is inductive in nature. When VC is greater than VL, circuit is capacitive in nature. And when VL is equal to VC, your circuit is resistive in nature. So here what is happening, in case of inductive circuit, voltage is leading. In case of capacitive circuit, current is leading. And in case of resistive circuit, your voltage and current are in phase. Voltage and current are in phase. Okay, so voltage and current are having phase difference of 0 degree. Okay, so this is regarding the phase angle of RLC circuit. So friends, we will quickly summarize what we have seen in phase difference. So our RLC circuit consists of inductance and capacitance both. Okay, so whether your current is leading or voltage is leading will be decided by the magnitude of VL and VC. If VL is greater than VC, circuit is inductive. So for inductive circuit, current will lag. If VC is greater than VL, current will lead because your circuit is capacitive. Okay, so current is leading. Okay, now we are taking first case. Suppose VL is greater than VC. So what will happen? Circuit will be inductive. So if you want to write the equations for voltage and current, so what is the standard equation of voltage? V is equal to Vm sine of omega t. Now since our circuit is inductive, so definitely voltage is leading and current is lagging. Okay, so how you will write current? I is equal to Im sine of omega t, and since current is lagging, we have to subtract phi. So this minus phi indicates that current is lagging. Okay, so here after omega t we are having nothing. Nothing means what? Here we are actually having omega t plus 0. So this plus 0 indicates what? Voltage is starting from 0 degrees, and this minus phi indicates that voltage is starting at 0 degree, but current will start after 5 degrees. Okay, so what we after looking at this equation, you can predict that current is lagging. So if we are getting minus, then it means it is lagging quantity. Okay, and if you want to calculate this phase difference, then we are having this formula. So phi is equal to what? Tan inverse of difference between VL and VC divided by VR. So tan inverse of VL minus VC upon VR. We know the values of VL and VC. IL, I into XL minus I into XC upon R. If we take I common, and in the numerator and denominator both sides we are having I. If we cancel I, what we are getting? Phi is equal to tan inverse of XL minus XC upon R. So this is nothing but the phase difference between voltage and current for RLC circuit. Okay, and this phase difference will be decided by XL and XC. Okay, and XL and XC are decided by values of L and C. So if your inductor and capacitor values are changing, what happens? Your phi value is ultimately going to change. So this is regarding phase difference for RLC circuit. Now friends, next parameter we are focusing is power factor of this circuit. Okay, power factor is very important parameter. What is the formula for power factor? Cos phi. And we have already seen that what is another formula for power factor? R divided by Z, means resistance upon impedance. Okay, so R divided by, and what is the impedance we are getting here? Square root of R square plus XL minus XC square. So what is the value of XL? XL indicates inductive reactance. Okay, so what is inductive reactance? 2 pi F into L. And what is capacitive reactance? 1 upon 2 pi F into C. So if you carefully compare these two reactances, what you will find here, XL is directly proportional to frequency and Xc is inversely proportional to frequency. So what happens? If your supply frequency increases, your inductive reactance increases. But at the same time, if supply frequency you are increasing, XL is increasing, but Xc will go on decreasing because frequency and Xc are inversely proportional to each other. Okay. So friends, what we can write? XL, inductive reactance, is directly proportional to the supply frequency. Okay, but at the same time, capacitive reactance is inversely proportional to frequency. Okay, so if you are increasing the frequency, your Xc will go on decreasing. If you are increasing the frequency, XL will simultaneously go on increasing. Okay, because they are having direct relation. Okay. And again, one thing you have to remember, power factor will always vary between 0 and 1. So maximum value is 1 and minimum value is 0. And this value will be decided by what? It will be decided by the values of resistor, then inductive reactance and capacitive reactance. If any one of them is changing, your power factor is definitely going to change. Okay. So friends, by the time you know that there are three possibilities in RLC circuit. First possibility is VL greater than VC, second is VC greater than VL, and third is VL is equal to VC. Now we will discuss what is exactly happening in these three different conditions. So first case, if VL is greater than VC, definitely XL is greater than XC. So the difference XL is greater than XC. So difference will be what? Positive. If difference is positive, definitely your phase angle is positive and your circuit will be what? Inductive. And we know that for inductive circuit, current is lagging with respect to voltage. Okay. Now if you take the second condition, VC is greater than VL. So what will happen? If VC is greater, definitely XC is also greater. So XL minus XC, this difference will be what? Negative. And if difference is negative, your phase angle will be what? Negative. Why phase angle is negative? Because we already seen that what is the formula for phase difference. Phi is equal to what? Tan inverse of XL minus XC divided by R. So if this difference is positive, definitely your phi is what? Positive value. If this difference is negative, definitely your phi will be what? Negative value. Okay, so same you are getting here. If your difference is negative, your phi is what? Negative, and in that case your circuit will be what? Capacitive. Okay, and if circuit is capacitive, we know that current is leading with respect to voltage. Current will be leading with respect to voltage. And if we consider third case, if VL is VL is equal to VC. So if voltages are equal, definitely XL is equal to XC. So difference between them, this difference XL minus XC is equal to what? 0. If we put 0 over here, so what you are getting? Your phase angle will be what? 0 degrees. So your phase angle is what? 0 degrees. And in that case, we know that when your phase difference is 0, your circuit is purely resistive circuit. And for purely resistive circuit, voltage and current are in phase. So your voltage and current are in phase. So these are the three different possibilities in your RLC circuit, and they will depend upon this VL and VC, voltage across inductor and capacitor. Okay. Friends, our next parameter is impedance. Impedance is nothing but the opposition to the flow of current by R, L and C components. Okay, so this I have written over here, resistance offered by the circuit to the flow of current, and we have already derived this value. So what is the impedance? Impedance is nothing but phasor addition of resistance and reactance. So what is resistance? R, and what is reactance? XL minus XC bracket square. Okay, so this you can also write like this. What I said just is your impedance is phasor sum of resistance and reactance. Okay, resistance and reactance. So phasor sum is indicated by bar. Okay, so Z bar is equal to R bar plus X bar. Okay, so if you want to remove this bar, you have to take square on both sides. So it will look like this. Z square is equal to R square plus X square. Now you are having two different X, XL and XC. So what is your Z square? Z square is equal to R square plus, and we know that XL and XC are opposite to each other, so we are taking their difference, XL minus XC bracket square. Okay, and if you remove this square, what you are getting? Square root of R square plus XL minus XC bracket square. Okay, so you can write equation like this, or you can write equation like this. Okay, both are same. Friends, our next and important parameter is power. This is very important parameter, because for any circuit, what is the power consumption? That is major issue. Okay, so we are having three different components over here: resistor, inductor and capacitor. So what is your average power? Your power will be what? Combination of power in resistor, power in inductance and power consumption in capacitor. If we combine all of these three, we are getting the average power for complete RLC circuit. Okay, so friends, we know that what is power? Power is nothing but V into I into cos phi. Okay, so now we are having three different parameters. If we are considering resistor, then you have to consider voltage across resistor, because current is common for resistor, inductor and capacitor. Okay, so if you are calculating power for resistor, then you have to take VR. If we are taking power for inductor, then VL. If you are taking power for capacitor, then you have to take VC. Okay, so power in resistor will be what? VR into I into cos phi. For inductor, VL into I into cos phi. For capacitor, VC into I into cos phi. Now we know that what is the value of phi? The value of phi is what? 0 degree for resistor. Value of phi is what? For purely capacitive circuit. For purely inductive circuit, value of phi is 90 degree, and also for purely capacitive circuit, value of phi is what? 90 degree. Okay, so put these values. So what is cos 0? cos 0 is nothing but 1. What is cos 90? 0. Again cos 90 is what? 0. So these last two parameters are contains 0. They are multiplied by 0, so their value becomes 0. And here you are getting 1. So VR into I into 1. So what you are getting? Your total power consumption is what? VR into I. And according to Ohm's law, what is VR? I into R. Okay, so multiplied by I. So what you are getting? I square R. So this is nothing but the power consumption in RLC circuit, and it consists of only resistance term. So what does this indicates? Although we are having three different parameters R, L and C, the power is consumed only in resistance. Okay, inductor and capacitor will not consume any amount of power. Okay, why? Because they are energy storing element. They are not power consuming element, they are power storing element. Okay, and whatever this power consumption occurs, this is nothing but active power. So active power is always measured in watts. So whatever power consumption occurs here, it will be measured in watts. Okay, so this is the average power of RLC circuit over one complete cycle. Okay, so it is nothing but I square R. Now next parameter is power curve. We already derived the power for this circuit. Now we will see power curve, means it is the diagrammatic representation of power. Okay, so for that purpose, first we should draw the waveforms for voltage and current, because what is your power? Voltage multiplied by current. So if you want to draw the waveform for power, we should first of all draw the waveform for voltage and current. Okay, so friends, now we are having three different possibilities. First possibility is VL greater than VC. Okay, so when VL is greater than VC, your circuit is what? Inductive circuit. So we know that for inductive circuit, voltage is leading. So this is the waveform for voltage. Voltage is starting from 0 degree. And since your circuit is inductive, current is lagging. So current will start after some time. Okay. So your waveform for current will look like this. Okay, now we are having waveform for current and voltage. Now what we have to find out? Waveform for power. Okay, so friends, if you consider this much area, what you will find out? Here voltage is rising and current is actually negative. Okay, so voltage is positive, current is negative. So positive multiplied by negative, what you are getting? Negative power curve. From this point to this point, in between these 2 points, what you will find out? Voltage is positive, current is also positive. So positive multiplied by positive. So what you are getting? Positive power curve. Okay, from this point to this point, what is happening? Current is positive, but your voltage is what? Negative. So positive multiplied by negative, you will get negative power curve. Okay, from this point to this point, what is happening? Both voltage and current are both are negative. Okay, so negative multiplied by negative, so what you are getting? Positive power curve. Okay, so this is your power curve for RLC circuit, and in which case when VL is greater than VC, means your circuit is nothing but inductive circuit. Okay, similarly we can draw the power curve when your VC is greater than VL. When VC is greater than VL, circuit is capacitive in nature. Okay, so suppose voltage is starting from 0 degrees like this. So since your circuit is capacitive, what will happen? Current is leading, so current will start somewhat earlier. Okay, so this is nothing but the waveform for current. Okay, now we want to draw the power curve for this. So from this point to this point, what you will observe? Your current is positive, but your voltage is what? Negative. So positive multiplied by negative, so what you are getting? Your power curve is negative like this. Okay, from this point to this point, your voltage, your current is positive as well as voltage is positive. So positive multiplied by positive, so what you will get? Positive power curve. From this point up to this point, your voltage is positive but current is what? Negative. So positive multiplied by negative, power curve is negative. So from this point to this point, both voltage as well as current both are negative. So negative multiplied by negative. So what you will get? Positive power curve. Okay. So this is nothing but the power curve for RLC circuit when your VC is greater than VL. So if you compare both power curves, what you are observing here, your starting power is negative. Okay, and here your starting power is positive. Okay, when your cycle is starting, initially your power is positive. Here when cycle is starting, initially power is negative. This is because in first case circuit is inductive, in second case circuit is capacitive. Okay, now again there is meaning to this. When your power curve is positive, it means what? Power is going from source towards the load. Okay, power is flowing from source towards load. Okay, means power is getting consumed. So this is nothing but the power consumed. Okay, and when your power curve is negative, when your power curve is negative, what does this indicates? When power curve is negative, what does this indicates? Whatever power stored in inductor and capacitor. So inductor and capacitor are nothing but your load. Okay, so power stored in the load will be given back to the source. Okay, so negative power means what? Power is returned by the load to the source. And power curve is positive, it means what? Power is delivered from source towards load. Okay, so this is the meaning of power curve. Okay, so now if you compare, negative area is lesser and positive area is larger, it means what? Less power is given from load to the source and more power is given from source to the load, and this is nothing but the power consumed. Whatever positive part you are getting, this power is getting consumed by the resistor, and this negative power is nothing but the power stored in inductor and capacitor. Okay, so this is the meaning of this power curve. Now our last parameter is nothing but impedance triangle. So for sketching in impedance triangle, first of all you have to draw the phasor diagram. So we will see the phasor diagram. Now we are having two possibilities. When VL is greater than VC, obviously XL is greater than XC, so circuit is inductive. And another possibility is VC is greater than VL, so in that case XC is greater than XL, so circuit will be capacitive. So first of all we will draw the phasor diagram for both cases and then we can draw the impedance triangle. So this is your current and voltage across resistor. Now here VL is greater than VC. Okay, so VL minus VC will be positive. So this is your phasor diagram. Now what we will do, we will take horizontal projection from VL minus VC, we will take vertical projection from VR, and whatever cross section point we are getting, we are connecting these to origin and cross section point. So what we are getting? Final voltage V. Okay, so this is phasor diagram for when your VL is greater than VC, means inductive circuit. Okay, similarly if you are drawing phasor diagram when VC is greater than VL, so this is your current, this is what? Voltage across a resistor. Now VC is greater than VL, so VL minus VC will be what? Negative. VL minus VC will become negative because your VC is greater than VL. Okay, now we will draw V. So we will take horizontal and vertical projection and then we will attach origin point with this cross section point, we are getting V. Okay, so if you compare these two phasor diagrams, now what we are doing, we are taking VR like this. So this is your VR. Now instead of taking VL minus VC over here, what I am doing, I am shifting it here. So what I am getting, VL minus VC. Okay, and in between these 2 points what you are getting, this V. Okay, Now what is the formula for this? I into XL minus I into XC. Okay, what is this? I into R. And what is this? Total voltage. So total voltage is what? Total current multiplied by total impedance. Okay, if I take I common over here, what I am getting? XL minus XC. Okay, so if I cancel I from all these three sides, what I am getting? R over here. So you can look at this. I am getting R over here. Then I am getting this XL minus XC. So this I am getting over here, XL minus XC. And on this side, if I is cancelled, what I am getting? Z. So this is nothing but your Z. Okay, so this is nothing but your impedance triangle for when your VL is greater than VC. Means when your circuit is inductive, you are getting impedance triangle like this. Similarly, what I am doing for the second case, I am shifting this VL minus VC over here. So what I am getting? So this is your VR. VL minus VC I have shifted over here. So VL minus VC, and in between these 2 points what you are having? V. Okay, so V is nothing but what? I into Z. What is VR? I into R. And what is VL? I into XL minus XC. If I cancel I from all these three sides, what I will get? R on the top side, so like this R. Then Z on this hypotenuse side, so Z on this hypotenuse side, and XL minus XC on this opposite side. So this is the impedance triangle for capacitive circuit. When VC is greater than VL, your circuit is capacitive and your impedance triangle will look like this. Okay, so phase angle is positive when circuit is inductive, phase angle is negative when circuit is capacitive. Okay, so in this way you can draw the impedance triangle for RLC circuit. Okay, in both cases, when circuit is inductive and when circuit is capacitive. And in the third case, when VL and VC are similar, okay, so in that case your voltage and current are in phase. Okay, so in that case we cannot draw any impedance triangle. So impedance triangle can exist only when your circuit is either capacitive or inductive. When your circuit is purely resistive, you cannot draw impedance triangle. Impedance triangle can only be drawn for inductive circuit or capacitive circuit. Okay, so this was about RLC circuit. So if you are having any suggestions, any queries, you can ask me in the chat box. uh, if there is any mistake in this, please let me know. I will rectify it. Okay, so thank you very much for your support. Thank you. Have a good day.